Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So today, here we go. We're going to be doing another video, and this one is going to be on what? None other than one of my favorite subjects, because really, I am a biochemist at heart. And so this worksheet is going to be on hydrogen bonding. This is hydrogen bonding worksheet number one. There'll be two worksheets, but this is the first one that we'll be going over here today. So before you watch this video, I am making a couple of assumptions. And one of those assumptions is that you have to have already watched my covalent bonding videos, that whole playlist, be familiar with the periodic table, valence electrons, and shapes, and all that kind of good stuff. So without further ado, let's see if we can zoom on here just slightly a little bit more and hammer out this worksheet on hydrogen bonding, the first one in a series of two. And then there's a lab that I do have that I've designed that's associated with this same topic as well. So here we go. Part one, the water molecule. Number one, draw the Lewis dot structures of water. One where the hydrogen and oxygen are at 90 degrees, and one where the angle is 180. So first of all, we do need to know the formula for water, and that is H2O. And how many hydrogens are there? There are two hydrogens. How many valence electrons in hydrogen? Well, there's hydrogen on our periodic table. How many valence electrons? One. So that would be 2 times 1. That is 2. How many oxygens are there in water? Well, there's a 1 right there. So there's 1 oxygen. And how many valence electrons are in oxygen? Here we go. There is oxygen, and there are 6 valence electrons in oxygen. So that would be 1 times 6. That is 6. And then what we're going to do is we're going to sum these numbers up. That's 2 plus 6. That is 8. And then, like I always do, the crazy hat chemist, what does he always do? He divides all of them by 2. And the reason for that is I just can't count very high, really. Yep, sad thing. So 8 divided by 2 is 4. So that's what we're going to work with. We're going to work with 4 pairs of electrons. Okay. Now, you do need to know the rules for how to place these. Okay. And in order for you to really fully understand this, you do need to have a copy of my covalent bonding handout number 2. In the second half of this talks about Vesper theory, and also you should be watching my honors chemistry unit 6. It's called the covalent bonding collection, or sorry, the bonding collection, and you would be watching bonding video number 11, Lewis dot structure rules. So I'm actually using these Lewis dot structure rules and following the set of directions to come up with the number of valence electrons and figure out what element goes where. So the first rule in placing the atoms is, well, you need to have summed up the electrons like what we've done. And then what we do is we do a plus sign or the sign of a cross. And I'm going to do this here just like this. I do this in pencil here because we're going to erase that really doesn't belong there. Okay, so the first one is going to be a 90 degree. And so the first rule, the central atom is the least electronegative element, but never hydrogen. So what's the most electronegative element? That is fluorine is the most electronegative element. So the one that's furthest from fluorine, and that would most commonly be hydrogen as opposed to oxygen. However, the rule is the least electronegative element, but never hydrogen. Consequently, hydrogen is not in the middle. So therefore, the oxygen is placed in the middle, just like that. Then we place the other elements, those are 2 hydrogens, in the 3 o'clock and in the 6 o'clock positions. Perfect, just like that. Now we have our 4 pairs of electrons which we must distribute. And so the first rule is to place a bonding pair of electrons between the central atom and the outside atom. That is viewed as a line. Then that's 1 pair. Then I have a central atom and the outside atom. That's also a single line. That's another pair of electrons. Okay, I'm going to rest the plus sign or the sign of the cross here because that just gave us the format in which we're following. The next rule is to place a pair, lone pairs of electrons on the outside atoms, and that would be like this. And unfortunately, hydrogen, or fortunately, hydrogen follows what's called the duet rule. And that is hydrogen only has 2 electrons around it. So 2, 4. That's 4 electrons, and therefore we cannot place lone pairs of electrons around a hydrogen like that. Therefore, we need to fall back to the next rule. The next rule is to place lone pairs of electrons on the central atom, and that is done like this. Then I'm going to verify the duet rule. That is 2 for hydrogen, the duet rule, that's 2 for hydrogen, and the octet rule for all other elements, or the vast majority of them except for boron and beryllium. That's 2, 4, 6, and 8, and that's validated with that. That's perfect. So that is the correct Lewis structure for water. Now we're going to do another Lewis structure for water. And that is, we still have the sign of the cross, remember that, or a plus sign that goes in the middle. And then what we're going to do is make sure that this bond angle is 180 as opposed to the 90, which we just drew. So we're going to have a hydrogen here and a hydrogen here. We could have had them at the 6 and 12 o'clock position, but we did at the 3 and 9. It doesn't matter. Same rules, bonding pair of electrons between the central and the outside atoms. Then lone pairs on the outsides, but I can't do that here, so I'm going to put lone pairs on the central atom just like that. The same set of rules apply. That's a duet rule for hydrogen, the duet rule for hydrogen, and the octet rule for oxygen. That does apply. This does look like this has a bond angle of 180, and this does look like this has a bond angle of 90. All right. Fantastic. So now what we need to do is we need to do problem number 2. And it says, what is X structure? What is the X structure? So what is the X structure? So we got to figure out that. So in order to figure out that, you need to have my worksheet. So let's see if we can figure that out. So this is the worksheet. It is the covalent bonding handout number 2. And so we need to figure out the X structure. So X. So A is the central element. This covalent bonding handout number 2 goes over the rules of that. A is the central element. That is the oxygen in both cases. X are the elements that are physically attached to the central element. So that's 1, 2 hydrogens or 1, 2 hydrogens. So that's AX2. The E's are the lone pairs of electrons solely on the central atom. So that's 1, 2 or 1, 2. Either way, either Lewis dot structure gives you the AX2E2 structure. So that's good. That looks fantastic. Everybody's happy with that. Now it's number 3. What is the name of the shape or the molecular geometry of water based on the X? So we're looking at this, AX2E2. Then you're going to go to my covalent bonding handout number 2 and find AX2E2, and that's right here at the bottom. It has 2 bonding domains, 2 non-bonding domains. The structure is angular or bent. So I'm going to write angular or bent. It's either one. It could be angular or bent. You can use one or the other as far as that goes. Number 4, what is the bond angle of this shape? And then again, you are also using my handout here. What is the bond angle? It is 105 degrees. So the bond angle is 105 degrees. So this is actually, knowing that this is 90 or 180, neither of these are correct. So we're going to erase both of these because the bond angle is actually 105. It's not 90. It is not 180. Number 5, based on the above molecular geometry, angular and bent, and bond angle, 105, which of the above Lewis structures is incorrect? Cross it out. This is the Lewis structure that is most incorrect, so we're going to cross this one out right there, just like that, okay? So knowing this, I want to go over one thing here, and that is making sure that this bond angle right here is 105 degrees. It's not actually 90 like what it looks like. I know that's what it looks like because we are drawing a three-dimensional object on a two-dimensional sheet of paper. If you go to my covalent bonding unit, you will find that we have built a bunch of models. So here is the model for water. And let me turn this around and make sure that you understand this, flip it around and stuff like that. It's very important that you follow this, okay? And so let's take a look at this. So the red thing right here, that is the oxygen. The gray things are the bonding electrons. So these are the bonding electrons between the oxygen and the hydrogens. The hydrogens are the white things. These tan things here are the lone pairs of electrons on the central atom. So you can clearly see that this bond angle here, this bond angle is not actually 90. It's more spread out than 90, certainly. It's 105. And you should see that that works out very nicely. All right, let's scroll this on up so we can do some more of the questions. Okay, and the next one here is number 6. Is water polar or non-polar? So the rules for polarity are as follows. Number 1, you have to have polar bonds. That's either polar or polar covalent bonds. And you need to have an asymmetry in its molecular shape. And one of the things that I teach in my class, and this is the keep it simple, stupid method, okay? And that is once you build the model, and this works for the basic models, it does not work for the hypervalent models or ones that exceed the octet rule, but it works for your basic model system until you really truly have a strong understanding of what's going on. But here we go. Are my fingers touching the same colors or the same elements? That's the question. The answer is no, since I am looking at all the things that are surrounding the central element. In this case, it's the red oxygen. Am I touching the same thing? If I am not touching the same thing, then it is asymmetric and polar. So that means that water is polar. And really and truly, water has a polar covalent bond and it is asymmetric in its geometry, and that makes it polar. So a couple of things that we'll get through here, and we'll discuss all of those in just a moment. Number 7, it says look up the electronegativity value of the oxygen atom, and you can find this online or on specific periodic tables. It will be 3.5. This is the Pauling scale of electronegativity, and for hydrogen, that is 2.1. What is, let's scroll this up just a little bit more here, and it says, what is the difference in the two electronegativity values? So we're going to take the difference, which is a subtraction. We'll get 1.4 for our electronegativity difference. So what does that mean? Number 9, it says, an ionic bond has a difference in electronegativity greater than 2. That is not the case here. A polar covalent bond has a difference in electronegativity between 0.4 and 2. Yes. So this is a polar covalent bond. A covalent bond has a difference in electronegativity between 0 and 0.4. That's no. What type of bond occurs between the oxygen and the hydrogen of the water molecule? Well, that difference in electronegativity is between 0.4 and 2. That's 1.4. And so it's a polar covalent bond. Perfect. All right, let's scroll this up. We got some more questions to do. Of course, of course. Okay. Number 10 is when a molecule is both asymmetric, i.e. polar, and has polar covalent bonds, there is a molecular charge separation within the molecule. This molecular charge separation is noted with a delta positive. That's the Greek letter delta. It's the lowercase delta, unlike the triangle, which is the uppercase delta, and a delta negative, which can be summed up by drawing a molecular dipole. Draw a molecular dipole in the Lewis dot structure of water above using an arrow. The point of the arrow is negative and the feathers are positive. So let's go back to our Lewis dot structure that we did not cross out. So the most electronegative element, based on our electronegativity values, is the oxygen. So at this end is a delta negative of the molecule. For hydrogen, it's a lower electronegativity value, and so at that end, it's a delta positive, just like that. So what we're going to do is we're going to draw a molecular dipole. That is a dipole for the molecule. And that's going to go straight through this like this with this arrow. That pointy part of the arrow is pointing towards the electronegative region. And so this whole region right here where the oxygen is and the two sets of lone pairs of electrons is negative. And then this area right here is electropositive. Excellent. You guys are doing a fantastic job. So if you can draw a molecular dipole, then that molecule will be polar. That's one of the key aspects of that. So hopefully that makes sense for you. That means it has polar covalent bonds or polar bonds, and it is asymmetric, and then that would be a polar molecule. All right, so let's keep on moving on. And let's do part two. So that was part one. Now we're going to move to part two. Okay, so part two is right here. All right, fantastic. Hey, a quick little advertisement by our sponsor. And our sponsor is none other than the Crazy Hat Chemist. That is me. So I'm sponsoring this video, and hopefully that works for you. Please like, subscribe, give me the thumbs up, hit the bell. You know what to do. You know, pass this video and other videos on to your friends. Hey, I have some really good cooking videos as well. So check those out. Those are pretty good as well, if I don't say so myself. I have the best pasta sauce in the world, the best bread in the world as well. And there'll be some future videos. I'm going to make some hazelnut and almond milk here pretty soon, homemade, organic. Oh, that's going to be delicious. All right, so let's keep on moving on. Thank you for our sponsor, the Crazy Hat Chemist. Really appreciate him. Thank you, thank you. Here we go. Part two, multiple water molecules. Number one, when two or more molecules interact with each other, the attractive force between, and I'm going to highlight this, I know I have it in italicized, but between molecules is called an intermolecular or IMF, intermolecular force. The intermolecular force between two or more asymmetric molecules is similar to the attraction of two magnets, where the positive end of one is attracted to the negative end of the other. In chemistry, this attraction is called a dipole-dipole interaction. Draw two magnets indicating the charge of both ends and the interaction between them. Okay, so I'm going to show you this as a demonstration. I think that's really important. I have two magnets. I've labeled them. There's a red end and a blue end of the magnet. The red end is positive, and the blue end is negative. So there's a black line there, that's a negative, and there's a positive right over here. So if I were to place this single magnet right here in the rectangular section here and move this positive end of this magnet close to that one, then you should see that's a repulsive force. I can spin this magnet around and try the negative end of the opposite magnet and move it close to it. And you can see that that is also a repulsive force. I'm not actually, you can see that my other hand, I'm not touching the other magnet. Nope, I'm not. Okay. And then if I were to turn this second magnet around, you can see that they are attracted. These two magnets are attracted electrostatically, and that is opposites attract, and that's an electrostatic attraction. So we're going to draw this. So we're going to draw two bar magnets, just like what I've shown you right there, and we're going to draw the interaction between the two of them. Okay, one end is going to be positive, just like I have. One end is negative. The attraction is when it's positive and then negative. And then this is the interaction between the two, whether they're far away from each other like this, or whether they are actually physically attached with that electrostatic attraction. This is called an intermolecular force. That's an IMF. Okay, so an intermolecular force is an electrostatic attraction between two objects. And we can see that clearly with this bar magnet. Okay, number two of part two, a special kind of dipole-dipole interaction, and this is a dipole-dipole interaction that you see here, occurs when a hydrogen atom is polar covalently bonded to a highly electronegative atom, most commonly either a fluorine, an oxygen, or a nitrogen. There can be other elements, but most commonly. And interacts with an electronegative element on a different molecule. This is called, yes, that's right, the famous, the one, the only hydrogen bond. Okay. All right, so let's take a look at some more examples of hydrogen bonds in water and see how that plays out. So what we're going to do is we're going to flip this over and we're going to take a look at the backside of part two of this worksheet. Okay, so let's set this up. Here we go. Number 3 of part 2. Draw Lewis structures of two water molecules and draw a hydrogen bond as dots between the two water molecules. And indicate the following in your diagram. A polar covalent bond. B, a hydrogen bond. So what we're going to do is we're going to follow the same setup of which we did on the front of this worksheet. And that same setup was drawing a water molecule in the same fashion with that 105-degree bond angle. Looks like 90, but you know it's not. So that is, there is our central oxygen, and here's our hydrogens right there. And polar covalent bonds, lone pairs of electrons, and we have to draw two water molecules. So this is kind of like what I'm going to do is I'm going to take this and I'm going to make a stamp out of this. And then I'm going to stamp another water molecule right here, just like it. Okay, perfect. That's what we're going to do. We're going to mimic what I have drawn here. That's that oxygen, the hydrogen, and polar covalent bonds, and then lone pairs of electrons, just like that. So I got two water molecules of which I've drawn. All right, now what we're going to do is we're going to draw the interaction between them. This is the interaction between them. The number of dots is immaterial. This is labeled as a hydrogen bond. And that is a special case of a dipole and dipole-dipole interaction. That is like these two magnets here. There's one water molecule, here's another water molecule, and boom, they're attracted with that electrostatic attraction because both of these have a molecular dipole to them, a molecular dipole. And those dipoles are in the same orientation, just like the two magnets are. Okay, so I've labeled the hydrogen bond that is in red. Now I'm going to label the polar covalent bond. And we'll say polar covalent bonds. Here is one, here is a second one, here is a third one, and here is a fourth one. So in water, how many polar covalent bonds are there? There are two per water molecule. Okay, awesome. Hopefully that looks good for you. I'm just going to highlight this region here. And in a hydrogen bond, what do we have? We have a polar covalently bound hydrogen. That is a polar covalently bound hydrogen. Okay. A hydrogen that's polar covalently bound will hydrogen bond to an electronegative element on a different molecule. That's what that is. Okay. All right. Perfecto. All right. What we're going to do is we're going to scroll this on up and we're going to do problem number 4. Number 4 of part 2 says the following: draw Lewis structures of 3 water molecules in one box and then 4 water molecules in the other box, with 1 water molecule in the center, and draw the hydrogen bonds between them. All right, so I'm going to go back to this very first picture that I drew, and this was the first water molecule that I drew, okay? And that's kind of my central water molecule, if you will. I'm going to do the same thing in problem 4 and problem 5. So the first water molecule I'm going to do is this oxygen here, a hydrogen, and polar covalent bonds and lone pairs of electrons. And I'm going to just lightly draw a circle around that central water molecule. Then what we're going to do is we're going to draw 2 other water molecules because we need a total of 3 in this box here. So I'm going to draw a water molecule right here, just like this. And notice that I'm using that stamping method, stamped, stamp, and I'm just mimicking exactly what I had before. Okay, perfecto. And then we have a choice that we have our central one right here. We've put one to the right. We can put one right below it. We can put one, and that would be at the 6 o'clock position. We can put one at the 9 o'clock position, or we can put one at the 12 o'clock position. All that matters right now for this activity is that we actually have 3 water molecules. So it doesn't matter where we place them. We've placed this central one, and we have another one here off to the right. I'll put one right below here, not that it matters where I place it. So it's entirely up to you where you would place it. All right, and now what we're going to do is we're going to draw the hydrogen bonds between them. And I'm going to label those. So H bond, and that would be right there and right there. Notice that the number of dots is immaterial. So the number of dots is immaterial for the hydrogen bonds. Polar covalent bonds would be as follows. There's one here, and here, and here, and again here, and again here. Okay? So what you see is this central water molecule hydrogen bonded to 2 others. Now we are going to do problem number 4 in the next box, which is 4 water molecules. And so what we're going to do is we're going to do a similar thing of what we have done already before. We're going to have our central water molecule. I'm going to place this a little bit higher just in terms of space-wise here. Polar covalent bonds, 2 sets of lone pairs of electrons. I'm going to circle this. This will be my quote central atom, central water molecule. And I'm going to stamp this, and I'm going to stamp another water molecule here in the 3 o'clock, then in the 6 o'clock, and then in the 9 o'clock position, respectively, in that order. Okay. All right. Hopefully that works for you. And there we go. So here we go. Polar covalent bond, 2 sets of lone pairs of electrons, that oxygen and the hydrogens, and polar covalent bond, and 2 sets of lone pairs of electrons, oxygen, hydrogen, polar covalent bonds, 2 sets of lone pairs of electrons. So now I have 4 water molecules, and then these red dots would represent my hydrogen bonding. That's a special case of a dipole-dipole interaction. Hydrogen bond in red, and polar covalent bond in blue. And there are many of them. I'll just label 2 of them. Perfect. Well, it looks fantastic. I'm hoping that you see some trends here on this. Okay. Now, the next one that we're going to do is we are going to slide this on up. We're going to do problem number 5. Now, um, there's a couple of parts to this problem number 5. So don't think that we're done. We are not done because hopefully you have noticed that there are some questions that we have not answered. Okay. So, booyah, I am the one and only, the Crazy Hat Chemist. And please, a note from our sponsor again, the Crazy Hat Chemist. Please like, subscribe, send these videos off to your friends, your family, even in other countries. I would greatly appreciate that. Okay, number 5, we're going to draw Lewis structures of 5 water molecules with 1 water molecule in the center and draw the hydrogen bonds between them. So what we're going to do is we're going to do that same thing that we've been doing all along. We're going to make a stamp and we're going to have that central water molecule. I'm going to circle that so that you can clearly see which one is my central water molecule. That's water molecule number 1. Number 1, I'm number 1. You're number 1. You're number 1. You're number 1. That's right, folks. Okay, so here we go. We're going to take this and we're going to stamp this and we're going to go 3 o'clock, 6 o'clock, 9 o'clock, 12 o'clock, high noon positions. You know what to do. You can probably do it before I am done. Okay, and so I will try to do this here quickly because you're going to do it faster than me. That is the goal, is to do it clearly and faster than me. All right, that's 2 water molecules. Here's 3 water molecules. And finally, the 4 water molecules that are surrounding for a total of 5. I'm going to draw the hydrogen bonds as these red dots. Again, the number of dots is immaterial. It's that we are drawing the red dots as the special case of a dipole-dipole interaction. That's a hydrogen bond. And there are how many? 1, 2, 3, and 4. This is actually the maximum number of hydrogen bonds that is possible in a single water molecule. So I'm going to now highlight this central water molecule. What is the maximum number of hydrogen bonds that can form on one singular water molecule? Maximum of 4 hydrogen bonds. And then polar covalent bonds. And I will just highlight a few of these polar covalent bonds there like that. Okay. Now we are not done. We need to do a few other things, and I'm going to show you another model. Okay. A, indicate the state of matter of water for all the Lewis structure drawings on this worksheet. So we're going to have to flip this over, and we're going to label the state of matter. So you see that both of these water molecules here, these are both by themselves. There's no other water molecule near it or surrounding it. So this is in the gaseous state. Gas. This is a gas. Okay. Gaseous state. Single water molecule. How many hydrogen bonds? 0 hydrogen bonds. Boom. None. 0. That's not an oxygen. 0 hydrogen bonds in the gaseous state. Flipping this over for problem number 3. We have 1 hydrogen bond that would be in the liquid state. Now, this would be a very, very special water molecule here, this central one, if you will. And this water molecule would have to be on the surface of the water. So if we have, let's say, a cup of some kind, here we go. And we have our water here. And the water molecule that is on the surface that is touching the edge of the container. So it's touching the edge of the container and it's on the surface. Then the minimum number of hydrogen bonds, since they do vary and break and change positions, would be 1. So this is a liquid. Okay, cannot be a gas, but it's a liquid, very unusual. Now we go to drawing number 4, where you have either 3 water molecules or 4 water molecules. Here you have 2 hydrogen bonds. So I'm going to draw this, and we also have over here in this next one 3 hydrogen bonds. So we have 2 hydrogen bonds, that's a liquid. And over here we have 3 hydrogen bonds, that's a liquid. So if one were to ask you how many hydrogen bonds in liquid water, I would say between 2 and 3 hydrogen bonds. It would be very, very rare to have this single one right here. So this is rare. Okay. So if given a question on a assessment of any kind, I wouldn't say 1 hydrogen bond for liquid. I would say between 2 and 3 hydrogen bonds in a liquid. Okay, and then we have number 5. And how many hydrogen bonds? Well, what state of matter is this? We have maximized the number of hydrogen bonds in water. And when you maximize the number of hydrogen bonds in water, then what happens? That is in what state? As the solid state. We know that as ice. Okay, so this is the maximum number of hydrogen bonds. That's very critical. All right, I'm going to show you a model. So don't go away. Don't think you're done. You are not done. Okay, hold on just a second. So I have another molecule or model, excuse me, to show you. And that model is right here. So these are water molecules or represent water molecules. The red represents the oxygen, just like this one did. Okay, right here. And the whites represent the hydrogens, just like this other one. What it doesn't have is it doesn't have the lone pairs of electrons, and it also does not have the polar covalent bonds that are in gray. What it does have, however, are magnets inside, and these magnets are in a special orientation. So let's follow this here, and you should see that this water molecule is very similar to that yellow central one, and I'm going to place this one right next to it. And what you should see that there's a hydrogen bond between this hydrogen right there, this oxygen on another molecule right here. Boom, perfect. And then what we're going to do is, again, this is our central. So we have one in the 3 o'clock position. We have one in the 6 o'clock position. Then we have one in the 9 o'clock position. And then we have one in the 12 o'clock position. Now, these positions are on paper, but you should see that this is following a like tetrahedral arrangement. Okay, so that is the maximum number of hydrogen bonds. Now, when this happens, then water expands, and you should understand this. You form a hexagonal, that's a 6-membered ring. Okay, and I'm going to show you that right here. Here is a 6-membered ring. Got 1, 2, 3, 4, 5, 6 water molecules, and that's a hexagonal crystalline structure. Crystalline because it's a solid, and it's maximized the number of hydrogen bonds per water molecule, which would be 4. I'm not showing all of them right here, but what I do want to show you is this central region right here that's on this central region. There's this giant gap here, and that means that water is in the solid state. If water is in the liquid state, then this is what is occurring. So we have hydrogen bonds all over the place, okay? And what water molecules do is they break and form hydrogen bonds, just kind of like this. That's why water is constantly always in motion. So they're breaking and forming hydrogen bonds. That's why we can say there's between 2 and 3. But once you reach a certain temperature, and notice how compact this is, there's very little space in here. So you're breaking and forming hydrogen bonds. The water is moving, okay, but there is no open cage structure. Okay, when you maximize the number of hydrogen bonds, you form an open cage structure, just like what I have here. And that increases the volume of solid water, otherwise known as ice, and therefore ice expands. And you know all those wonderful properties of ice and that it floats. Why does ice float? Well, it's because this open cage hexagonal hex for 6, hexagonal crystalline structure. All right. So hopefully that worked well for you. Hey, please like, subscribe. I appreciate you watching my videos. I greatly appreciate it. I am the Crazy Hat Chemist, and I greatly appreciate your time. Hopefully you are actually learning chemistry, and thank you for hanging on for such a long period of time on this video. And I do truly hope that you learned some good chemistry. I'll talk to you next time. I got another video on hydrogen bonding. That's video number 2, and we have a lab. Hopefully you're in my class, and if not, you should come on over to my class and take my class. I'll see you next time. Bye for now.